Okay, so more examples of using Newton's laws to solve these problems. All right, so now I've got a situation where I say I have two boxes which are next to each other on a table. So they're touching each other on the table. And I'm going to push on the side of one of them, and that's going to make both of them move. And they're both going to move with an acceleration, and I'm telling what the acceleration is. It's 1.5 meters per second squared. And I want to know what is the amount of the pushing force. And I also want to know what is F12. What is the force of box 1? Oh, sorry, what's the force on box 1? On box 1 from box 2. Right? Because they're right next to each other. So that means that they're going to have a force. What's the interaction force between the two of them? So I'm going to go ahead and I'm going to draw some pictures here. So let me just draw a little sketch of how I see this. This is not my actual what I'm going to do all my forces on, but I'm going to say this is box 1. And by the way, here's the masses. Mass 1 is 10 kilograms and mass 2 is 20 kilograms. So this is going to be my mass 1. And here right next to it, touching it, is going to be our mass 2. So mass 1 and mass 2. And they're on the ground. And we're going to have no friction right now. So I'm going to push on this guy, right? Here's my F push. And I'm drawing my boxes this way. I could have had everything flipped and had the other way. Again, that's up to you. If you drew this another direction, had everything moving to the left instead of everything moving to the right, that'd be fine. Because I'm expecting that these will then accelerate this way, where the acceleration is this 1.5 meters per second squared. So that's just my take on how this looks. Now what I'm going to do is I'm actually going to draw separate boxes for both mass 1 and mass 2. So this is mass 1, and then mass 2 will be here. Even though they touch each other, I'm now going to draw them separately to try and get a better handle on what forces are on mass 1 and what forces are on mass 2. Now, mass 1 actually has the pushing force. And although it's pushing and touching the left side of this, I'm going to draw that force coming out of the right side. When I draw my forces, I want the tail of the force to touch the box, not the tip of the force to touch the box. This will make things cleaner in my diagrams. Mass 1 has a mass, so it's going to have m1g coming down. It's on a surface, so it's going to have a normal force. Now I'm going to have two normal forces, right? This guy's also going to have a normal force, mass 2. So I need to call this F normal 1 or something. I've got to distinguish between them. This normal force is not going to be the same as this normal force. So over here, when I go and draw these forces, this is going to be the normal force 2. So I've got to distinguish between them. So that's the pushing force, the normal force, and the gravitational force. But box 2 is touching box 1. And in fact, that's what I'm asking for, is what's the force on box 1 from box 2? Box 2, if box 1 is pushing into box 1, is pushing into 2, that means that box 2 is pushing back on box 1, right? Hopefully that makes sense to you. So those are the forces on that box. Here On mass 2, I still have gravity, but this is m2g. Now this pushing force, now I'm pushing on m1. I'm not touching m2. And if I don't touch m2, I am unable to exert a direct force to m2. So the pushing force is not exerted on mass 2. What is exerted is the opposite force, the equal but opposite force of force 1, 2. There is force 2, 1. This is the reaction force. So that force 2, 1 has the same magnitude as force 1, 2. And we can see that the direction of F1, 2 is opposite the direction of F2, 1 is opposite of F1, 2, right? These are opposite forces. This is going in that, what I would call the negative direction, and this is in what we call the positive direction. And that brings me to my next thing, which is I'm going to explicitly say in both these pictures what the positive and negative directions are. Or the positive directions, and that implies the negative directions. I'm also going to sit there and say, hey, I already know the acceleration. In this case, the acceleration is this way. That's actually a sub x, right? A sub x in both of these drawings is 1.5 meters per second squared to the right. And then I'm also going to say that a sub y is 0, right? These objects are not bouncing up and down in the y direction. They're just, sitting there. So I have these pictures. How much space did I leave myself over here? Let's copy these pictures and drag them over to the next page. So we have them over there. Let's see if I can draw this. Here we go. Copy. Okay. And let's put them over here so we can look at them when we try to do Newton's laws here. All right, so this is looking a little more complicated. Again, I want to do F net equals m, in this case, m1a. And then I also want F net on mass 2 is equal to its mass times its a. In both situations, I have x, or I have horizontal motion, I have horizontal forces, and I have vertical forces. And so again, these really turn into F net y's and F net x. F net y is not that long, so I can probably put it a little closer up. F net y, F net x. Again, even though the two blocks are right next to each other, in this situation I need to separate them and talk about in terms of what forces are on M1 and then what forces are on M2. And then they each get their own F net equation. You don't treat them like one, you treat them separately. So then if I look at this picture up here, in the y dimension, I have the normal force 1, and then I subtract off m1g. That has to equal m1 a sub y. This is F net y, but a sub y is 0. And so, perhaps not surprisingly, the normal force here is just the weight of the block. I'm going to get the same rough looking thing when I do over here. I'm going to have F net 2, normal of 2, minus m2g equals m2 a sub y. Its a sub y is also 0. And so the normal force of the second block is also just its weight. Okay, so then when I do the x parts here, if I look at this diagram, F push is in the positive x direction. So I'm going to say F push minus F12. Those are the forces in the x dimension. I don't have to split anything up with cosine and sine this time. That has to equal mass 1 times the acceleration. The acceleration is this 1.5 meters per second squared. Now I don't know F push. In fact, I'm trying to find out F push. And I also don't know F12. I'm trying to find out F12. And so I have to leave this equation as it is right now. And I'm going to go to the last equation I can make, which is the F net x on mass 2. All that I have is F21. That's the only force. There's no other force, right? If we look at our blocks, there's nothing impeding the motion to the right on mass 2. Gravity can't do it. Gravity's pulling down. There's nothing over on this side to slow it down. There's just F21, which is the force of the first block on the second block. So I have F12, and that equals m2 times ax, but ax is the 1.5 meters per second squared. And so I can get here, F12 should just be mass 2, which was the 20 kilograms, times the 1.5 meters per second squared, which is 20 times 1.5 is 30 newtons. Now the magnitude of F12 is the same as the magnitude of F21. And so this amount right here, F, that tells me that this equation, F push minus 30 newtons. Now I don't have to worry about the fact that the direction of F21 is different. The direction of 1,2 is already written in this equation. That's what the negative is for. The negative said F12 is in the negative x direction. So all I have to do in here is put in the magnitude, and the magnitude is 30 newtons because the amount of this force, these are equal but opposite reaction forces. So the amount of this force is 30 newtons, the amount of this force is 30 newtons. That has to equal the mass 1, which is 10 kilograms times 1.5, which is 15. And so I get the F push is 15 newtons plus 30 newtons, or 45 newtons. And then I look at that and I think, does that make sense? If I go back and I look at my diagrams, F push is 45 newtons, F12 is 30 newtons, and so is F21. So the net X force on mass 1 is 45 minus 30 newtons, or 15 newtons. It takes 15 newtons to make this 10 kilogram box go 1.5 meters per second. That's second squared. That's absolutely true. Here it takes 30 newtons to make this 20 kilogram, twice the mass, so it gets twice the force to go the same acceleration. When you come out of these equations, you'll get numbers. Here I'm getting 45 newtons, 30 newtons. That's the magnitudes of the forces. When you get forces out of your equations, It's going to be the magnitudes of those forces. The directions of the forces are drawn in your picture, right? The direction of F12, I get that because I've already drawn a picture that shows the direction of that force. F21, F12, F push, F normal 1, F normal 2. The directions are in the pictures. What I get out of the equations are just the magnitudes. In each of these examples, I'm following the same steps, the same method. For each separate mass, I'm drawing a box. First, I draw a box. So again, for each separate mass, so the first couple of ones, we only had one mass. But that last example, there were two masses. There was mass 1 and mass 2. They each you have to do all these steps the same for each one. So I had to have two boxes, one for mass 1, one for mass 2. If there's a surface, I generally include the surface as a straight line whatever side the surface is on. After you have your box, then you're going to draw arrows with the tail touching the box for each force. So you'll ask yourself what force acts on mass 1. I know all the forces that are acting on it, and if they're actually forces, you draw arrows starting with the tail on the box and going in the direction of the force. Then, although I did this usually afterwards to try to get you to understand why we need to do it, you do need to explicitly pick what's going to be your positive x and your positive y directions if it's two-dimensional. If it's just one dimension, if you only have horizontal, then you can just do positive x. If you only have vertical, you can just do positive y. But if you have two dimensions, you need to have both, and you should draw arrows for that. But again, they don't touch the boxes. These are just showing us I'm going to have off to the side. This tells me what I'm calling positive directions. And the last arrows you draw are which way do you think the object is accelerating? You should, if you think it has an acceleration in the x direction, you should draw an arrow for the direction of it. If you actually know that amount, like we did in the last problem, then you should include that as well. If you think it's accelerating in the y direction, again, draw an arrow for that. If they're not accelerating, if you know they're not or you think they're not, then you should write out that the a sub x is 0 and the a sub y is 0. And those should also be included in this picture. So there's a lot of things that go into this picture when we're doing it. Once we have our picture, which by the way, this is a free body diagram. These four things together, these make up what we call a free body diagram, which I usually write like this, FDB, free body diagram. Once you have your free body diagram, then you're going to use the forces in the pictures to figure out what your F net x equation is and what your F net y equation is, where you add the x parts of the forces all together and you say that has to equal the mass times the acceleration. You add all the y forces together and you have to say that equals mass times the y acceleration. If you have a force which is in two dimensions, it's not completely x, it's not completely y, like we did for that tension force where we had the tension off at an angle of 35 degrees, then you're going to have to split that force into an x part and a y part, and those go into their respective F net y and F net x equations. At the end of these steps, I'm left with equations, and I use the equations I get from these steps. That's the equations I use to solve for whatever the problem is asking me for. But I can't even get to what the problem is asking me for until I've done all of these steps. Now, I have, over the years, realized that it's better to type up these rules for force problems, and so they're on this next page. They're also in the homework practice questions. There's an attachment, which is the file for this as well. if you follow the rules for forces, the ones that I've just gone over, you can solve any force problem, and it can get nasty ugly. It can be far more than you think it's going to be when you first look at a problem, but you can solve anything, any force problem, if you follow these rules. And again, so here's the rules written out and typed. Basically, it's a little wordier than what I wrote down by hand, but the ideas are the same. You're going to draw a box or a circle or a dot that represent your object. I'm always going to do a box. You're going to draw arrows with the tails touching the box for each force that acts on that object. You're going to decide if you need, how many dimensions does your problem have? Does it have only X forces? Does it have only Y forces? Or does it have both X and Y? If you have 2 dimensions, then whatever dimensions you have, you need to choose a positive direction and show those with arrows and label them. This is when I say do positive Y, positive X. And really, you can pick anything here, but if you have 2 dimensions, the 2 dimensions have to be perpendicular to each other. They must be at 90-degree angles. So in other words, you can't have positive Y and positive X, right? That's not a 90-degree angle between the 2 of them. You have to have 90 degrees between them for this to work. For each dimension, so if you have X and Y, then you need to do this for both A sub X and A sub Y. If the acceleration of the dimension is 0, write it down. So A sub X is 0 or A sub Y is 0. If it's not 0, then draw an arrow labeled with that A sub X or A sub Y, showing the expected direction. These last 2, the arrows don't touch the object because they're not forces. Only the arrows which are forces touch our actual object because they're the things that can make the object move or accelerate. Again, these top steps produce a free body diagram. After we have that, we're going to do our F nets, where we add up all our forces in a certain dimension, and so that equals the acceleration times the mass in that dimension. All right, again, I'm going to stop this video before I move on to the next one, where we're going to do a couple more common situations.